I feel very sad about it, but does everybody understand? Was that useful? Are we ready to get this show on the road? I'm okay. I'm looking for the Discord. I'll just how how do I don't usually use Discord that much. Okay, it's over here. Yes, yes, yes. Everybody's good. Ah, you're recording. Good. Thank you very much, my good man. So, so yeah, so not all is lost. Hopefully, you got the audio as well. So that's the summary essentially of the whole module and how things are structured. I'll give tips. So what to expect for this session is that I'll give tips on how the questions would be asked and how to approach them. I also do have YouTube videos, but the only YouTube videos I don't have for is chapter 9. That's the one that I've not had the time to record for. So hopefully I got a recording of my own here. Yeah, the recording of my own. So we're just gonna go through examples, and if you have past papers, I don't have any papers in particular as well. But I can go through the ones that I posted here. You can still post questions if you want, like exact like explanations for each bit as well. So I try to explain that as well. So with all of that said, let's start with chapter 9. Okay, I thought this was the magic eraser. Start with chapter 6. Chapter 6. So chapter 6. So now that you have your tree, you've generated your syntax tree, and it's you have I just need something to reference off. Okay, I don't. Okay, yeah, I don't know what happened. I don't have the select tool. Um, yeah, I just do this. Okay, so I just have to do that. So I'll just, okay, now why did I copy it? I'll just take it as a whole. All right. So chapter 6, you've went through syntax analysis, you've uh, made your parser, and now you have a tree over here, a tree. So the goal of chapter 6 is not that you've got your tree over here. Let me just at the tree from chapter 2, and the scope table from chapter 3. Chapter 3, I don't think there's ever been an exam question on chapter 3. Uh, I'm not sure I'm not, I don't, at least before 2023, there wasn't any questions on chapter 3, but it's usually just scope analysis. And this is where you just give your language a personality, per se, where you decide if what type of how it handles scoping and how naming is done, whether variables can have the same name or not. So you process your syntax tree and you extract information. So chapter 3 usually does scope analysis. I'm pretty sure this was covered in what's that module 33, I believe, in programming languages, I think so, where you're taught you're taught about the different types of languages and the way they handle properties. So that's the only useful thing from uh, from course 333 that would be applicable for compiler, in my opinion. But that's just me. Uh, so you learn about the different types of languages. So that's what chapter 3 is about. So, but if I imagine a question being asked, if I was Professor Gruner, I would probably have this as like a theoretical question or like a multiple choice question where you get quizzed such like how would what would a scoping language like this have? And also I would have it as a practical as part of the project as well, where I just say for our language here it is statically typed or dynamically typed. So but that's at least that's all I can say for chapter 3. But expect anything for the coming exam. And for chapter 2, I have a video on that, but we can cover that tomorrow if you guys want. Chapter 2 is just you just generate this. And now for chapter 5, now that you've done all of that, your goal and you want to do chapter 6 intermediate code generation, your goal is to take this whole tree and you want to generate, let me just exaggerate. Is there you go. So your goal here is to generate new code. So you want to convert this syntax tree into code, essentially, at least intermediate code. And the way you would do this, you can, the way the textbook does it is that instead of writing code, it makes use of these tables over here. These tables. And let's see. So the language that we're translating, so let's see, the language that our target language also has a grammar. Let me go look at that. Target language grammar. Also, just while I'm just scrolling through, it's also useful to have some of the tables here. So while I was writing the exams, having just the tables was useful as well. At least it's something to reference off, and also the grammar. Example language for interpretation. I don't. Could this be it? I don't think so. Too sure. Okay. Example language for interpretation. I think this might be it. But I'm not too sure about that. I'll just copy it just in case. Somebody can correct me if I'm wrong. 'Cause I'll just have this here, but I'll still look. Let's go to chapter one. Page one. Chapters. I'm just looking for the grammar for the language. A small example language. Now I'm back at the same place. All right. I cannot find it. Let me just go through here. So that's the intermediate language, and yeah, I don't have. If somebody can find the in the source code language, but all I know is that these tables over here, they're based off the intermediate. Did I get a message? Might be page 154. Let's see, 154. I think this might be it. Let me think about it. It could be. It could be. Yeah, I think so. Expressions. Yeah, I think that might be it. I think that might be it. I remember it being much bigger, but it could be wrong. Okay, so translating an expression. So yeah, yeah, good, 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 good. Thank you very much. Sakura, Sukur. Yeah, but yeah, thanks again. So here's the intermediate language over here. So you would have your source language over here, then you'd have your intermediate language over here. No, you'd have your the tables. So the way these tables are made from the textbook is that, let me just write this down. So this is the source code language, or EFG. Uh, EFG. And the way the textbook does it is that for each non-terminal, there's going to be a table for each non-terminal. So this table, the first table over here, this one, where's the pen tool? Let me just press P. So this table over here is for this non-terminal expression over here. And this one, expressions, will have its own table as well. It's going to be expressions, expression. So this whole table over here. And for each rule, we're going to have a case where we translate uh, from the rule, we translate that token or that branch into this. So for each case, we'll have, for example, for rule one over here, we'd have this case or this row, and the last line of the row will be our translation. Each function takes in parameters over here. So this trans, it stands for translation or translator. Um, and it's for the expression, and it takes in an expression, it takes in this tree. So you can imagine we're just passing in this entire thing over here, and then it will try to match this with a rule. So let's say we're passing in, so expression could equal to expression produces num. And then we pass it in, and then we would match this rule over here, or this node, with this over here. And then with this, we're going to execute this code. And the way this code is ran, the last line is always the return statement over here. And the language that this is written in, this is pseudocode. So there is no like exact, at least from I'm not sure if the third edition does explain it even more, but we can think of it as pseudocode. You can also write Python or anything really, and you would get functions. So the functions that you would get would allow you to access, for example, um, a direct translation. So you would have, let's say, a dictionary value. Let's say we have our dictionary of sorts. Think of it as like a dictionary where it equals to, let's say you had a language where the value of 10 would get translated into 10 or so. Or and you'd have 7 and gets translated to 7. So we have like a sort of dictionary that is able to convert um, one like one thing from one language into something else. So in this case, it's called get value, but it doesn't have to be strictly this name. It can be anything. You can make up a name as long as the idea is there. Um, then you also have it takes in a num, which is like the value, and if we pass in 10 here, v will equal to 10. The word 10. I should have done. I don't know any other language other than English. Uh, I yeah, so I wish I could like translate something. Okay, maybe I know. This is the only thing I know. So if we pass in hello, it would, so which is like the English word, we'll pass out konnichiwa, which is Japanese, I believe. So that's how it would work. So in terms of programming, which is something I do know, if we were to translate, let's say, uh, what would be a good example? Uh, we can say a equals to if let's say you get the equal sign, right? You would translate it into EQ in another language. So in one programming language, it's this, but in another language, it's that. And so that's the whole idea. So does everybody get the idea of what a dictionary is? Well, so far, at least with like my explanation so far, any confusion? Cool. So, so you would have a function that can like return that would check. So this function only translates the values or the dictionary. So it does a direct translation. And then you would have place equals to v. And I do believe I have a video on chapter 6 that goes more into detail on how these work. But the idea is that you would have a function and it's able to do a direct translation from like a sort of dictionary, or it's not direct necessarily called a dictionary, but the concept is the same. And then you'd also have your v table, and your v table is just a table that has all of your variables, like let's say a, and all the values stored in those variables, like that. So in some cases, you would have, so this gives you access to the table that was generated in chapter 3 or so, and has all the values. And you also get another thing called your f table, which translates the functions, which translates the functions as well. So if you have like function f, your f table could be underscore f, or let's say you had the function add, but in another language, it's like this, something like that. So it's just the function names. So your v tables would be like this, and it would be like that. And in some cases, your V table could be like a direct translation of like the variable names as well. So if like let me just put it separately, like so. You have your V table. You're gonna have the letter X in one language, but you could translate it to like a different variable name, like something uh, maybe A, something like that. So, but normally in the textbook, if I remember correctly, uh, let's see. Yeah. I think in the textbook, interpretation is where you would use the values, but in translation, you would use this idea of translating the variable names. And I believe the textbook does have this idea over here where it explains so yeah, explains so it does so the symbol table. So yeah, it calls it the symbol table, the variable symbol table that binds X, Y, and Z to this. So this section over here, it explains just that. So the reason for this separation, why is a V table here like this and a V table in like in the an interpreter just the values? Because in an interpreter, you're trying to evaluate. So let me just go back to over here. So in interpretation, your goal is evaluation. And here in type checking, your goal is correctness. And here your goal is translation. So your goal, is your goal is translation. Well, because you're trying to get new output. You're converting one code to other code. Yeah, you're checking if the code is correct, like you're not assigning a string variable into an integer. And here your goal is evaluation, where you're trying to get a final output. An example of this is like Python as well, where you just want to get an output as well. So that's the goal. So here, so if you see a V table in interpretation, I'm not sure if that example still stands. I'm just doing this to double check. I don't want to if there are the so interpretation, do they have an example? Probably not, but let's see. Table. Okay, environment produces a functional F, which is a lexical. Is this the right chapter? Yeah, chapter 4. So V is an integer, and V is supposed to have some sort of value. Okay, I cannot find the exact example, but I won't dwell too much on it. So there's that. So here we would have something like this. So V table is the same as a symbol table. And an F table is also, again, a direct translation where a function name would be different and such. So back to this example, at least to rehash everything, you would have a grammar for your simple language or your source code language. So the grammar for each non-terminal, you would have a table and for each table, each row would represent the rule for that non-terminal, and you would map that rule. So the function would take in parameters. So it would take in example, which is you can also think of this as like the node if you were like programming it in a real language. And you have v table, which is your symbol table, your variable symbol table, or just and this is your function symbol table and you have your place. Place is usually a placeholder variable. Like it's usually just think of it as like uh, if you want to keep track of like the final output. So you have a function like you have A and B, and then you have like your output, or you have like something that you want to pass in, and then it returns. Uh, Actually, I think I might be explaining it very badly here, but you're gonna get a value that's passed into here. It's usually a variable name or passed code, and you're going to paste it over here. So you're gonna get like value X or something like that here, and then you just replace it over here. Then it returns that. I might explain it better in my video. Uh, so here you have code one. Where does code one come from? Okay, yeah. Does it? Okay, I might be explaining it wrong, but the whole idea is that you pass in a value that you want to plop in, and that's where these place variables come from as well. And the way these are coded, it becomes a programming problem where you try to interpret the tree, at least each row, and you would try to get different results. So, for example, the if this was like a node, it would look like this, where it's like exp would produce I forgot what unop stands for, maybe like this thing. And then you get expression one. So your code would receive this node over here, and you'd have to write code that can interpret this, that would check the child one, and then this would check child two, assuming that it had an array of sorts. And then you just process each one recursively as well. And that's at least like that's the idea of what chapter six. At least like that's how the tables work together. Um, yeah, that's how the tables work. It's very confusing. Most of us are used to writing like programming code instead, where we just write a whole function that does that for us. But the idea will still be the same. The textbook chooses to do this as well. So in the past, the types of questions that would be asked would be to make this table yourself. And the table, he when he mocks it, he wasn't strict on like you had to follow this exact syntax. You could make up your own, like for example, this new var function, you could have just said you could just write the full name new variable, or like generate variable name. The idea is still there, where it just generates a name or so. So he wasn't too strict on that, and I believe later on he's shied away from telling us to make the table, but instead he asks to write actual code that does the translation for you. And I believe I might have an example of that. The I did create a compiler just understand demo. Is this it? Okay. The mod that screen open like on my other side. I'm just opening the code. Open the project. But is everybody understanding so far? Is there like any confusion or such about chapter six? Mhm. Can you just check? So I'm trying to also like open recent project. Ah, yes, my cat language compiler at this window. All right. Okay. Ethan's good. Everybody else, you can do your reactions on the whiteboard as well if you're good. If you're looking at my screen, there you go. So I wrote a compiler that translates this over here. So it's just a simple language. So it takes in it was the idea was to have a language that a cat would write. It's a bit of a silly idea. But you'd have your parser, and then you'd have your type check over here. So your type checker, the code, normally you write it like this. So you're just traversing a node. So I tried to write it the same way we like at least as close to this as possible. As close to this as possible. So I wrote this just to so the yeah this gets translated into Java code as well. So this is how it would look like. You just pass in each non-terminal, I'd have a function that says translate that terminal, and then I'd pass in the node, and then for that node, since this is like each node would have like I'd understand what the code structure would look like. I believe I have the grammar over here. Um, even wrote the grammar. That language, I chose LL1 because that's the simplest one. So I chose a grammar that follows LL1. So I have program start and the start statement, and I just did the translations like this. I didn't do an intermediate. So for each child, in the node, I'd get the children, even though you're supposed to, this would have a single child or not. And then I just translate it down. I think this might be an outdated language. I might have updated it a while ago. But yeah, the idea is that you would have the node, you would traverse the node, and then you would go down. And since you'd understand the structure, you'd know what to do for each part. And yeah, that's how I wrote that. Yeah, this is definitely a different function call. I wrote this last year. I barely remember it at all. So yeah, that's the idea of how like the translator would work. So that's like the translate function, and the same here. So an exam question would ask you to would give you a grammar, and for that grammar, you'd have to come up with a translation for it. At least write a translation function or produce the table, which would be the exact same thing, but without the content. So you'd have to come up with this yourself. And yeah, you'd have to come up with this yourself. Like you just write down everything. Or I've seen that he gives you a function header and then you just write the actual function itself. And in the end, when you go through this whole process, you'd have an intermediate code such as this one. Get the text, copy this. Yeah. So once you go through this, I'm not sure if this actually translates to this over here. It doesn't look like it because it feels a bit too small to do that, but the idea is there. So you translate this, it would give you, you take this code, and the code would look like it would follow this grammar, and then from there you just it would give you this kind of an output that follows this grammar over here as well. So I think that's like my type of this that's how I would boil down chapter 6. um Fairly simple. I have a video that explains it. I'm not sure how well, like if it's still good for today, but it's still, I believe it was good enough like to take you through the whole shebang. So yeah, that's my summary. Does anybody have a question, or like any question paper that you want us to go through for chapter 6, or anything at all? And just to like let's see, YouTube, in case you just like you want the what YouTube video I'm referring to. Just you're going, so it's the first vid. It's the only video I was able to recover from my, at least from 2023, 2024 when I recorded it as well. So I'll just paste it over here in case anybody wants like an example, just going through it as well. Okay, and yeah, anybody, any questions or like that? Or is everybody good? You can also just drag and drop a question and be like, here it is, or something like that. My question with chapter 6 and 9 is that it takes long. My question with chapter 6 and 9 is that how do we do everything quicker? Okay, so let me just copy this, paste it over here. So Ethan asks my question. So chapter 6 and 9 do take an annoying amount of time to do. And my suggestion for how to do it faster is to, okay, the only way to do it, to do chapter 6 faster without following the tables. Okay, before I answer this question, right? Let's actually like summarize what types of questions can be asked for chapter 6, right? Before I answer that, chapter 6, you're gonna get two types of questions. One question would be, um, let's see, given the following grammar, uh, write a write translation function for it over here. So you'd get a question that asks you to basically generate new code, like to write a translation function. And then let me just reduce the thickness for this one, if necessary. And the other type of question you would get asked is um, given the following, let's try to remember. So translate, yeah, given the following code, translate using the method from chapter 6, using the, translate using the method. So you get asked to do this as well. Okay. So these are the two types of questions. Let me try to think. If you've seen a different example, feel free to like add it. But these are the two main ones where you're asked to make the translation functions, or you're asked to do the translation itself. And then from the translation functions, it can boil down to um, uh, just you make a table for the translations, or write pseudocode, or like just write code. Uh, it could be pseudocode, like any kind of code. It's usually just pseudocode. Just write code. So okay, there you go. So yeah, when you get asked the question, it's usually these two kinds of questions over here, where write a translation function, and that function could either be in pseudocode or the table transitions. And given the following code, use the translation method from chapter 6 as well. So I don't think I've seen any other iteration, but I can imagine a different iteration of this. So to answer your question, how to answer faster, if you're asked to make the tables, like do the transition, I would suggest let's see, try having a copy of these tables on your textbook. Let me just refer to page 154. Okay, that's very useful. Page 154. Uh, So you'd have, yeah, you'd have your own. So I would suggest for me, what made it easier is having a copy of these tables onto your book. Onto your book. Okay, yeah, okay. I missed all. Okay, we could have just went through the book. Example of statement translation. Okay, okay, the book has examples. Pretty cool. I'll just have this on the side. I don't know. I should have went through the whole textbook. I just went through the parts, But yeah, the textbook seems to be much better than before. So I suggest having a copy of these tables, specifically transcon, at least these tables. Try to understand how they're written, because if you go through it, it's actually pretty simple. Like, try to understand how the all of these are written, and also realize that you have the freedom to write your own. So when he asks you to like make a table version of these, it's usually just copying the table from your book or the textbook and just writing your own for that language. So you'll probably be given a different grammar. And for example, you'd be given this grammar. So the question would be, given this grammar over here, write a translation to write a function, and you would just write an exact copy. So it'd be like a one-to-one copy, but you'd write it for that example grammar. And also another way I've seen these questions being asked is they'd add something else. He would add another question like, I don't know, I'm just gonna make up a rule. Condition, statement, condition. I'll just add expression again. Just so he'd give you a new rule like this, and it says something like uh, jump jump to jump jump to line. Okay, I cannot think of anything. He'd give you a new rule over here, and you'd have to make a table for this. And just for you try to use the context given to understand what does jump mean and what does line mean, and what parameters would I need to do that. And you can reference the tables, and usually most of the time it's usually just a direct copy, but you can also just make just write pseudocode and try to write it in a form at least similar to this one, where the last line is the return statement. And that's how. So for this, make a table for the translations, have a copy for. So I'm just using a different to do it faster. I'm just have a copy have a copy of the example tables. r- okay, I have a copy of the example tables in your notebook, and because most of the time it's a direct uh, copy. So uh, mm, to your answer sheet. So yeah, hopefully that makes sense. If that does not make sense for me, let me know so I can clarify a bit more. If some of you don't understand, you can just either Discord or that. But for this, just having a copy of the tables and having something to reference does make you faster. You know what I mean? And also understanding how it all works, at least using context, you'd be able to know which row to copy, or because it's either you're gonna make a whole table or just one table, or multiple tables or just one. And for writing the pseudocode, I've not had, I've not personally had like a situation where I had to write one, but this becomes a programming problem over here. So I don't have any good advice on how to do it, but other than like write whatever like pseudocode makes sense. Like so you just like given the context, because it's usually you're just passing in as like the code here suggests, like over here, you get passed in a node and you just have to figure out, okay, like how do I express that I'm getting a I'm appending like something like it depends on like the context. So you're just writing code. So if you're able to like write code, at least like be able to reason or logic how something would be done, like we would process this node or such. I'm moving my hands as if you guys can see me, but that's like the idea of how um at least when you're writing codes, it's a programming problem. So just you'd practice writing nodes, and that would hopefully make you faster, in my opinion. Well, if that doesn't make sense, you can just ask questions or like such. Um, Also, practice is also another thing that would make you faster. Practice with what? I think the textbook might have examples, but hopefully somebody has an example question, or else we'll move on to the next chapter. Uh, given the following code, translate using the method. For this, for me, this while I was mocking questions, like because during my time as a tutor back in 2023, Professor Karuna I would come up with the questions, and I'd no he no he would send me the questions, and I'd have to make up my own memo. So the way I was able to produce like a memo quickly is because I understood how the tables from the textbook work, because I've translated them so many times. So you might notice while you're doing a translation that, let's say you have the following over here. Let's look at a live example. Okay, so let's look at a live example. So you have this. They ask you translate this into this, right? You'd notice every time you say equals, f equals 1, right? You'd notice when you pass in like f, I don't think I have the tables over here. You'd always end up with like you're assigning the value 1 over here to a temporary variable, and then you would have v0. I think where is f referenced again? I think f over here. There's a translation. I think there was a table. So example. I think over here they must be converting f to f. So I'm pretty sure f, there's a translation where f equals to v0. But if let's assume there wasn't a translation table, you'd notice that every time you have an assignment, let's say x equals to 2, you'd notice that you'd be followed, if you were to translate this, it'd always be t1 equals to 2, and then x equals to t1. So you'd notice every time you translate this segment over here, it would always look like this. So for example, n equals to 7 would always look like this. So this over here is n equals to 7. Yes, and this. And I believe, so over here, if you look through uh, questions and notes, I sort of do make a reference to a website. This website over here, created by Daniel, really useful. Um, I published one of his websites over here. So you'd notice, okay, here, if you want examples, and I'll put this over here I'll put it over here in like the Slack link over here, and I'll also post it on the Discord channel. Again, for those of you. So what the way the website works is that it shows you an example of chapter 9 and chapter 6 translations. So he has this feature where you can like hover over a variable and it shows you like which parts of it. So but what I like about this is that you see input, right? The input here gets translated into that, and you see, and then the rest it just comes together. So this website, very cool. You can also like add it as well. So input. So this references the v tables as well. So the idea is that you would understand like certain structures. For example, you would see repeat f equals to f times n equals to this. You'd notice that repeat would always have like the same structure, would always be false. So there'd be a label and it'd be L1 and L2 and such. So you have to find the patterns. So does that make sense? Does that answer your question, like on how to do it faster? Oh, cool. And does everybody understand as well? Okay. Mm. Very nice that snippets of codes produce the exact same translations each time. So once you understand that translation, you don't have to go through the table to like produce the exact same because you recognize that that works. Um, but I'd suggest do the long method first, like just for practice, so that in case you realize you notice that you made a mistake. And also another way, I think this is also just like a question of mine. This is just like for me. Another thing, once you've done this, how do I know if a translation is correct? And for that, I would say the translated code follows the same logic as the source code. So if, like for example, uh, you notice that this is assigning 1 to f, 7 to n, and then repeat. So it's gonna repeat for this logic. Your translated code should do the exact same thing, and that is correct. And I believe that is what Professor Gruner does. At least when I was mocking it was either I was mocking the structure or I would mock the logic as well, just to see, because some people would do it differently. So your translate no the correct way is that if your source code does the same thing as your translated code, as well as your intermediate code. So this is also another thing to help you out to make sure that you did it correctly and you did not make a mistake, because compiler is one of those modules where you cannot afford to make a mistake. So it's always good to have a way to check if you did something correctly or not. And in this case, it's this. And in this case, you just check if does your translation make sense? So if you produce a table, just or you write code, does the logic, would it produce, if it started from the top of the tree and it made its way down, would it produce that? And yeah, that's that. So, okay. Is everybody good with chapter six? Is everybody all right with that? And awesome. I have a question. Awesome, we got a question. I have a question. Translation. You post. I have a question. I have a question about the intermediate translation in question you posted for chapter six and nine. In the main function for the statement call even one, I noticed that the solution doesn't store the parameter into a temporary variable before the call. I was expecting something like T0 equals to T1. Is this correct? Also, how strict is Prof with the amount of lines your code has? Because in the memo for 2025, he also mentioned the menu should be 22 lines and have. Uh, okay, let's see. I just post this over here. Okay, wrong spot. There you go. Use this. So this is just two questions. I noticed that. Expecting that. Is this correct? Okay, the solution I posted was from last year, so I don't know if it's correct. I trust that it's correct, but we can double check it right now. So you said when we were doing a call, even t equals to 0. Was this for the caller save or callee save part? Uh, Check caller save. Let me check the caller save. Okay, caller save, caller save. I should learn how to label these things. Let me just show this over here, and then let me just go to notes and resources, and I believe it was SLR notes chapter 90. Okay, not this one. Notes homework 3. Was it homework 3? No, not this one. Yeah, it was one of those question. Yeah, it's the one I posted, right? Yeah, under the questions tab. Yeah, it's this one over here. Yeah, but I'm having a hard time reading this. So I'm just gonna look at this one over here. So if that's okay, it's because I'm pretty sure it's the same thing. And this is the intermediate code. So you're asking what the intermediate code was. So what was the question again? I have the worst memory. So I noticed that I have a question, intermediate code translation, the question you posted for chapter 6 and 9. In the main function for the call statement, e equals even I, I noticed that the solution doesn't store the parameter into a temporary variable before the call. I was expecting something like T0 equals I. Is this correct? And over here, so when I generate the intermediate code, normally, let's see, you don't have to store it in a temporary variable since you're just passing it in. At least you would generate the temporary variable after, at least in chapter 9. So is just to be safe, this is the code you're referring to. Okay, this is the intermediate. Where's the call? Over here, call, and over here, call T6 equals to T6. Oh, even over here, I did put a temporary variable. I don't think. Hmm. Let me think about it. I don't think you'd need a temporary variable, but why would I put an I here as well? See. Actually, to be on the safe side, using a temporary variable, you can do it where you have T0. Either that or it was there or I cut it off. That could be a possibility as well. But yeah, in my opinion, you can have a temporary variable. At least I would suggest having a temporary variable stored before. So in this case, I'd say we're just missing that T0 equals to that. But I'd have to refer, let me double check the example in the textbook because the example in the textbook always provides, let's see, not Firefox call. I'm just looking for the example. Okay, yeah, the call and return. Okay, that's just chapter 9. Uh, there we go. So before the function call, so it doesn't call over here. It's T3 and T6. So in some cases they do. So okay, in my opinion, this is just me, right? I would not have a temper. I just pass in the values directly. As to why I pass it in, I think over here. Let me see. I think over here. Go back to this question. I think the reason it's like this, I'm pretty sure I must have had a line of code where I said t equals to this over here. Uh, there's this, this, this over here. So I believe what I did is that I just put this whole thing, at least like into the function, and I just translated it using the table. And yeah, there should be a temporary variable because we're saying e equals to that. Yeah, I think that you're very right. You're very correct, though. There should be. So I think it was a mistake. See, so it should be t0 equals to z equals to call and then even I something like this, and then the translation would be e equals to t0. Yeah, I think I'm not sure how I missed that, but yeah, good eye. That is correct. So it's supposed to be like that. Um, it's supposed to be like that with the rest of the translations over here. I think so. Yeah. I think so. So yeah, you're correct. So I'll just like add a thing. Just I'm can't see. Queen. Okay, I made a mistake. Translate the e call even to. Yeah, there we go. Yeah, it's so of do is correct. So I even wrote it wrong. I think it's supposed to just yeah, I think it's supposed to be this with whatever I think I. So yeah, so it's supposed to be something like that, right? Yeah. So yeah, it's supposed to be translated like so, in my opinion. So I think I must have missed it. So hopefully that answers. How strict is Prof with the amount of lines your code has? Because in the memo for 2025, so he's not too strict as long as the structure. So I believe Professor Gruner, he follows more the structure of the code. And if the structure is different, so when I say structure, it's like if you were to translate, for example, this over here into that. And let's say we did not have a function table. Another student might just put in like a different, instead of using T, they just write the whole word temp one, or like they use X0 or whatever they do. Even though like they're using different variable names, the structure is still the same. You're just replacing all of that. So he would check if does the structure match his memo, and if he doesn't, he would check the logic. And but if the structure is different, it's most likely that there was something wrong, a mistake, which would lose you marks as well. So he would just check that. Maybe his memo in this specific example, he had exactly 89 lines and 32 lines. And I remember when he was like giving me advice on how to mock the chapter 6 and chapter 9, he said just follow the structure. I follow the structure and the logic, and it usually how that's like the fastest way to mock 60 plus students or however many people are doing compiler. I think it's closer to like 150 or so. So so just checking the structure is easier, and then if the structure is different, we check where it's different and deduct the marks if the logic is not sound as well. So yeah, hopefully that answers your questions. Let's just go. Okay. So nobody else has any other question relating to chapter 6? Yeah, going once, twice. Yeah. Okay, we are okay. We're done with chapter 6. And naturally, the next chapter is chapter 9. Is everybody happy going to skipping chapter 8? Because we can do chapter 8 afterwards so that we carry on the momentum. Is everybody happy? That? That's cool. Awesome. So, yeah, you can save this board. I'll try to save the board. Uh, it usually does not work out for me, but I'll try to save the board so that you guys can reference it later. And that means I might have to delete one of my board, which is not a big deal, really. So, but it's so yeah. If you want anything else relating to chapter 6, okay, you can go to questions. You can post your question over here, and I can answer it so that everybody can see the results. Or you can like send me a message directly if you like want that as well. Okay, with that, let's move on to chapter 9, which is the continuation of chapter 6. And because chapter 6 does not complete the, I think this, uh, I just hate that I cannot like the select over here. So, chapter 9, what's chapter 9 again called? I think it's called functions or something like that. All I know is that it has to do with functions, that's all. And for chapter 9, I'm glad I have this open over here. Um, okay, chapter 9. So this was a slide. If you want the slide, the slides are in the resource section over here. So I'll just like basically be summarizing what I said and also just trying to explain. We can even do an example afterwards. I probably won't do it very well because it's been a while, but the idea is still there. But I think I can explain from the top of my head. Uh, okay, so I have chapter 9 functions, and the purpose of chapter 9 continues the translation, continues or yeah, the translation of chapter 6 by translating the call and return statement as well. So the call and return statements, the reason we have to translate those is because they do not again exist. So it's an assembly type language, the one we were translating to this one over here. So when we translate into this language, this is supposed to be assembly-esque, where evidence of that is memory access over here, and I'm pretty sure these would be registers. And I'm pretty sure assembly does not have equal signs, but in this case, we'll just like get a just. But this is just accessing direct memory, and this can be your registers. Your ID can be like R1 or R2 or R3, and but this over here, the book says it's not valid for this language over here. And so we have to translate this to make use of um, it is like call and return explicitly are not part of the language. So we have to replace them, at least we have to rewrite them into chunks of code. So the way to do that, we have to define certain concepts. So chapters 9 comes with new concepts. The first one is a call sequence over here. So your call statements. Okay, what's going on? Oh, yeah, it's because I have to. How do I do this? Okay. Okay, the website is very buggy today, but that's okay. So I'll just copy. Wow. Okay, that's really bad. Oh yeah, so I can just no. Wow. Okay, I do. So that has not happened before. So I don't know what's up because the website used to be a lot more responsive. So your call statements, you learn how to translate them into a call sequence. And then you have your return statements and you convert them into it's happening again. What? Yeah, yeah. Okay, what am I supposed to do here? Okay, okay, that's okay. technical difficulties at this stage is not good. Okay, I see. So you calls I see. So this your return statements get translated into something called the epilogue. Yeah, the epilogue. Uh, So retranslate this. So I'm just gonna put in translates to, and then your return statement translates to. And it's not just the call and return, it's also the function definition itself. So it's not explicit. So this as well, not this. Uh, the So your header as well, uh, this bit as well. We'd also have to translate it because not quote unquote part of the language. So we'd also have to translate this as well. So we'll call that the function definition. You have your function definition or your function header. It's the same thing really. And it will translate into the prologue, at least a bit of code. So the call sequence, epilogue, and prologue are just new bits of code that like do the exact same thing. Uh, so I just say so it translates to. So the goal, so this is the goal of like chapter 9. You learn how to do this. Okay. You learn how to do all of this, right? And the context in which you're doing this is in like the context of an assembly type language, assembly type language, assembly assembly type language with features like, so this thing would have registers, uh, jump statements, jump or go to statements. One, two, and what else? I'm trying to think of another thing. Jump statements and huh, labels as well. Labels. Uh, yeah, I think that's all I can remember for now. Could not be anything, but these are the bare bones. So in chapter 9, we learn how to do this. So we translate this call statements, return statements, and function statements into call sequence, epilogue, and prologue. And these are just blocks of code or snippets of code, but we can just think of these as like these are just the blocks of code, new blocks of code that do something. And the call sequence specifically, uh, they have it's just a sequence of instructions. All of these are sequence of instructions, but they do have like a defining instruction, like for example, the call sequence. Um, it sets the label for the return function. So the call sequence sets like it sets up where if we're like a label, it sets up a label statement that says this is the return so that once we call the function knows which label to return to. So it has an instruction that sets the label. It also has other instructions as well. But this is the most defining one. An epilogue, no, I don't have to copy for this one. So an epilogue, it's also a sequence of code and the most a sequence of instructions where we that's okay. I know I'm like an hour and a half into this session, but is my audio good? It's like I'm not like I don't want, I should have asked that at the beginning just to be safe. But is is everybody able to hear? Uh, okay, cool. So okay, that's good because if someone I don't know. Okay, so the epilogue so it has it's also a sequence of instructions, and the most defining instruction is a go to return function. So it knows what the previous function is, so it translates that And it also has other instructions as well. And those other instructions, so the other instructions usually involve variables, registers, and storing them in memory and returning them from memory as well. And so that's what the other instructions usually refer to in this case. And then we have our prologue. And the prologue, the defining instructions here is an is also a sequence. So prologue is also like a sequence of instructions, and the most defining thing about it is that it has a label for the call function, or the callee function. But we can just keep it plain English for now. Called or callee, same thing. Um, tomatoes, tomatoes. Bad pronunciation, but yeah, label. This is another and another one, another defining set of instructions that come after. So the label. This is the label of the function that's being called. So when we do a function call, we usually just sets the label. Yeah, yeah. So this also has a go to the call function as well. So this has this, and then the label it just has that, and it also has let's see, instructions for parameters for setting the parameter values. So it has instructions for taking care. So if we have a function, let's say f, I'll just do this. So let's say you have f, a, b, and c. We would have instructions that that would take care of, like, would translate these a, b, and c and store them into variables as well. So it would take care of that, and then would also have other instructions as well. All right. So that's how these are the three concepts that you would like, at least these are the main concepts that you would learn from um, chapter 9, call sequence and epilogue and prologue. And these are like the defining things about the the defining qualities, at least from my perspective. And we also have other instructions. And the reason we have other instructions and not like the set instruction is because those other instructions, like, because you'd have to decide on a strategy. Because if you're saving, the reason these exist is because now that we're dealing with registers, right? We have to registers, and another thing is that they also have main memory as well. So that's another thing. So it's registers and main memory instead of like variables. So you don't have unlimited variables. So you have to store. So an idea is that if a function is currently running, or if like a sequence of go, it would have registers that it works with. So a function would have registers. However, when it calls another function, the function would make use of the same registers. So if you've done assembly before, you would know that we have like other register like names like REX, AX, X. I'm not sure if X is like a valid one, but you just have like common registers, like common registers. Okay. PC, okay, you can obviously you have the program counter, but there are other ones that I want specifically. Um, okay, different x86. And, okay, so you have like these ones, these common variables over here. So these registers, you'd notice that as a function is running, it would make use of these. And there are a lot more. Like I think each language has like you can reuse some of them for different things or whatnot, but there are a limited number of them because the register is okay. There's 32 bits, and there's also, I think, there's 64-bit. Yeah, I think there's a 64-bit version. But the whole idea is that we have registers are fast, but we don't have a lot of them, which is why we make use of main memory. And main memory is usually in this textbook is represented by the letter M as well. And main memory is also like associated with like the stack. But huh, I'd have to be careful with my wording there because again, it's it's not that it's complicated, but I'm just trying to remember as I go. But we also have the stack as well. But it's the same as the main memory. Huh. We'll see later on. So, but yeah, you have your registers, and then you have main memory where you can save your registers and all, like they're past variables. Then you have the stack, which may or may not be part of the main memory, or it is the main memory. And then you have your jump and go to statements and labels. So that's so if we're dealing with this, and the other instructions that the prologue and epilogue and call sequence would have would use these differently depending on like where's the best place to like store the registers in main memory. So if I'm a function using registers, and then I know another function will also use the same registers, I need to save my own registers before it overwrites them. Because if we just jump from one function to another function without like saving or like we will lose those values, we'll lose those variables, and all the values will get overwritten, which is the last thing we want. So we have to take measures to prevent the variables from getting overwritten. So there are two strategies that come from these like that you could apply, at least more than two, at least two. The first strategy is that the function that is calling the other function. So I'm just gonna write it down. So we have the function here. Let's just call it function A, and let's make it a tad bigger. Okay. Then we have function B. So since we have these two functions, the first idea, okay, let me just also like have like just like have a bit of illustration. Um, I may okay, okay. Let's just have like the registers, and let's just emphasize that the limited, and and have like main memory. Uh, Abundant but slow. So there's like a lot of like space to store variables here. So limited but fast, you know. So function A would make use of like the registers, and function B will also make use. So function A, they can make use of registers because the variables are really fast and they can execute. But if they make use of main memory to store their variables, they would run much slower. So the idea here is that a function would make use of registers, and it also has the ability to save those the values in the registers into main memory and also retrieve them as well. So with that basic idea in mind, what if we wanted to implement something where function A could call function B? So what would that process like? What steps, what precautions to make sure that once function A calls function B and function B returns to function A, um, how would it keep the variables? And also, how would function B know how to return? Which function does it know to return to? So there's like a lot to consider. The first thing is that function A would the first thing it would do, one strategy, let's call this the caller strategy, where the function that is calling is responsible for all of that, you know, is responsible for setting up, is responsible for handling all of that, where the jumping and the saving of the variables. So we're just gonna call a save strategy. So we're gonna do call a save. So function A, what function A will first do is that it would like read the values. Okay, this is a very bad diagram, but so what function A would do is that it would read the values from the registers that it's using, and it would save all of those registers into here. So all of the values for the registers into here, and it would know which values were it saw. So it takes everything that it owns and then it puts it into here, and that it jumps to this, and then it also has a way to like say, okay, so it's gonna read the values. Let me just write all of this down. So what function A would do is that it would read all the used registers and save them into main memory. It's a bit too big. So, so using the caller save strategy, function A would read all the used registers and save them into main memory. The reason I emphasize used registers because a function won't use 30 all 32 or all the registers, so it will use some of them. So you can call these used registers active registers, used or active registers, which are the ones it's like using, um, and save them into main memory. And then two, it would set the value of the label into set the into like main memory, at least like see it would set let's just say it would set the value of the return label. So it would set up a label for itself, at least a way for to know for the next function that is calling it to know where to return, and then it would jump to function B. So it would jump to function B, and once like a function B, once function B receives that function B will just like function B will use the registers and 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 jump back, to function A. So it would do what it needs to do, and then it would jump back to function A, and function A will uh, restore the values from main memory into 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 the registers. So all the values that it put aside to save here, it would now put them back, right? And so that's how the caller save strat. That's the first strategy. Does this strategy make sense, everybody? Like, is everybody confused or like following along? We good? Okay, it's good. Okay, cool. So this is a like high level overview. So this is like the idea of what like it needs to do. We'll get into like the code bit in just a bit, but that's the main idea. So that's the first strategy it uses. Uh, Let me just drink some water. Mm, yeah, this is a bit of a water break. Mm. Just a quick question, just to query. Is anybody feeling tired or like you also like anything like that? Because I'm not sure. Like, I'm just staring at the screen. But I want to make sure. Is everybody okay? Is everybody doing good? Like nobody like being overwhelmed or such? Mm, yeah, it's all good. You can just use the reactions as well. So I'm gonna assume everybody's good. If like I'm not making sense or like I'll upload the video that's hopefully recording the right screen, and also like just the first few bits I forgot who was recording the first 15 minutes, but if you could share that bit as well, that'd be cool. I'll re-upload the video to the YouTube channel, and so that yeah, you can access it again, watch it, or you can also message me again as well, like privately, or you could post a question, or if you want like some notes on it, you can publish on the notes. All right, now that that's done, so that's the first strategy. That's the caller save strategy and such. So it has these things to do. At least that's what the caller save strategy entails. And then you're gonna have the other strategy, the callee strategy. Should I have them side by side? You just have them like this. There we go. And then same saving strategies. And there you go. Then just put them over here. And you just put them over there. All right. So so you're gonna have callee save. So this one, let me just add more to it. Function calling it is saving. Or the um, the function that calls is is saving. All right, so it's right there. Just to like simplify it even more. And the callee save, this one is a strategy where function A does not have to worry about it, or does not have to worry, uh, does not have to save like anything. At least it does not have to. It does not have as much responsibility. So we are gonna have callee save, where the function that is called is saving. And the way it would work is let's see, quite simple. Let's see. All right. So again, function A would jump to function B. And function B, that's not how you spell word. Yeah. Function B um, would read all the active registers of A and save them into main memory. And then function B, okay, now that function B has saved all the variables of that was used by function A, function B makes use of the registers. And then um and then once it's finished, when function B okay, let's see, before function B returns, it it restores the variables, or at least it restores the active registers of function A from main memory and jumps to function A. There you go. And then function A continues. And it's the same idea here. Where function A continues. So in this strategy, function A would call function B, and function B would read what variables, what registers was function A using. And then it would, once it sees all of the ones that we use, it would save all of those into main memory. And it would then start processing and make use of the registers for itself. And before it returns or like it jumps back, it's it goes back into main memory. It finds all the variables that we used, and then it would returns each one into main memory before jumping back into A as well. So that's the idea. That's how callee save works. All right. So these are the two main strategies of like saving. Because you notice that with these strategies, you do something before jumping to the next function, and then you access main memory, and then you put values into registers and restore them as well. And that's essentially so that's why these two strategies exist, and that's why like just do this. Okay. Okay. That's why these two strategies exist. That's like the main idea, and the way they work is that it's very, I think the textbook does a decent job at explaining that, but it's still, and from the lack of examples, it's still like a bit confusing. uh, but this is like the main, if you read it, this is like the main idea, this is what it's trying to explain, where these are the two main strategies. And the sections are, so that code, so now when we go back into this, right, you'd see that we have other instructions. Those other instructions could be either saving, like storing into main memory, or like so let me just write that down as well. Uh, the other instructions could let me just also highlight this so that you see. So the other instructions could be moving moving values between the register and main memory and jumping. And there's also something with the stack pointer, which I have not explained and will do as well. But this what else? Yeah. There's also like other things with the stack pointer, but we'll get to that in a bit. But that's the whole idea, and so you can see that with this idea in mind, right? Depending on the strategy, you could be saving your variables in the call statement, in the call sequence, or you could be saving that in the epilogue, or you could be like restoring or like restoring in the epilogue, or you're just returning, or in the prologue, you could be setting up the variables. You could be saving in the prologue, or you could just be like the prologue could just be concerned about that. So because of that, we're gonna have two types of called at least like depending on your strategy, your call sequence will look different, your epilogue will look different, and your prologue will look different. And I'm moving my hands again as if you can see me. But does that make sense? So does that whole explanation make sense? Is everybody good? Uh, all right. So let me just double check on the Discord. So yeah, no one's typing, so it's all good here. So these are the two main strategies, and depending on which strategy that you use, you're going to end up with like different call sequence or such. And we'll get to that. So these are the two main strategies. There are other strategies as well. There's also a like a hybrid. A hybrid. That's not how you spell hybrid. No. Hybrid. Right. Right. I think so. Um. Okay. Okay. So okay, it's just like a little bit of a story, just like a short story. It doesn't It's very irrelevant, but uh I was talking to Professor Nyati and he was like questioning my spelling and I was like, I'm doing computer science, not spelling science. And then he just rolled his eyes. So yeah, that's just a little story time. Okay, now back to business. We have a caller save and callee save. So you can imagine it uses these two strategies as well. So it hybrids like a where one part so this you can have it where this does the saving and this does something else or like just also that. Let me look at the textbook to see like what the other strategies. The other strategies are just derived from these two strategies. So call save where like parts of the registers like some sure so like this one like it removes all of the registers and just like a color save takes all the values like all the active values from the registers and stores them into main memory and but hybrid could also like reserve some registers for callee and others for caller so so that when we're like jumping from one function to another function, the caller would only save its designated registers as well. All that. So yeah, this is that. So that's hybrid. There's the other methods. I don't think there's the other ones have never really mattered too much. Yeah, that's like the main idea. Looks like they even have some examples as well. So yeah. So that's the two strategies. So how would this look like? So if you're in like a test situation and you are asked, let's see, use the strategies. How would the code look like? How would it like I'll explain using I think this slides over here. It does explain that. There's also something called the stack and the stack frame as well. And the moment I'm very hesitant to call the stack. First, I'd have to look at the example too. Understand myself? Yep. Okay. Uh, Call stack stores information about every function call. So now let's just go over here. So now that we've done all of this, right? Like this is just like a general high level overview. How does it actually do it, and how does like it actually work? And so for this, like for example, how is the information for like where's the return label set? Where like how does it know which variables to use or what values to save? Or like um do we tell it that no RAX or whatever? Where's that information stored? So all of the information here. So to both strategies, they make use of the stack, all right? And the stack, is the example of the stack is over here. Oh, did someone drop off? Yeah, hopefully it's not too bad. So you'd have the memory, the computer stack. Eh, hopefully it doesn't show me like a stack of computers. So you'd have your stack over here. Um, looking for like a nice, useful like example. Available stack space. Okay, I think this might be it. I don't think the textbook has an example of a stack, so I have to use a general image, but I could be wrong on that. I don't think so either. Like, yeah, I don't. Does not exactly have an example of the call stack. But so we just you can just think of it as like this. So yeah, you have your stack over here, and you'd see that like your stack is like upside down. So your stack would start off over here, and then it would like go all the way down. So that's how most stacks. I'm pretty sure the stack in the textbook works the same way. And in your stack, if you've done stacks before, you know it's just a data structure where it follows the last in, first out strategy, where the last thing that was put in is the last thing that's like gonna get put out. And so, and you know that each thing that it stores is a node. And in our case, the nodes are called frames or a stack frame. And a stack frame stores information. So parts of like memory over here. So this could be a stack frame, this could be like another stack frame, and this could be another stack frame, and this could be another stack frame. So the stack frame is like a let's see, stack frame is the data structure that is stored in the call stack, which is also just a stack data structure, just stack data structure. And your data structure would look different depending on what strategy you're using. So your stack frame would look different if you're using Colo or Coli save because you would like save information differently as well. Because in one you wouldn't have to worry about something else and such. So it differs per strategy. So that would be your call stack. Let me just follow along this example as well. And each element is called a stack frame or activation record. It's also called an activation record, and it has passing function variables or parameters, and storing the return address memory for non-local variables. So we're just storing the variables that are not part of like the that are not part of the currently called function, and allocating arrays and records. So it's just stores information for like necessary for a function to like to do its job. And in our book, each activation record is stored in memory. So luckily I wrote that. So our call stack, our stack is stored in the memory. And what else? A stack pointer points to a memory address location in the stack. So with our stack, the variable that points at an element is called the stack pointer over here. So it looks at the memory address and such. So I think I'm just trying to look. Yeah, yeah, that's it. So I'll just emphasize more on this because how you generate code, like depending on how, because your stack frame may look different depending on how many like how much data it has. Uh, so, for example, you might have, because if it stores, if a stack frame stores per function parameters, how does the number of parameters like change the size? And that's it, the answer is usually yes, it does. So some stack frames are bigger than others because of that. So you'd have to do some stack mathematics or memory mathematics or memory arithmetic, something like that, to figure out how much memory to take in. For example, if you have p number of parameters, that means you're going to need like if you have p number of parameters, uh, you'd need this many like objects or this much memory to store over here, something like that. But we'll get into it hopefully if I remember correct. We'll see once we like actually doing it. So your stack frame will look different depending on which strategy you use, and yeah. But the order also matters as well, because if you're like subtracting, that means you're like adding something, so you're going down the frame instead. And yeah, I think that's all I have to say. But if you want, let's see, I'll try to find a YouTube video because I know there was a YouTube video that would explain it much better. You don't need to understand. Okay, you kind of do need to understand how the stack works, at least how the stack frame works. Let me do a quick Google search, YouTube search for that. Let's see, call stack. Like, let's see, that should be because I know there was a person. How assembly? Okay, I think yeah. This video really
top of
good.
mains, right, to his base. So now the register has
Okay, yeah. This video I'd recommend it if you want to understand more on the stack. These because an intuitive understanding of it would be beneficial for chapter 9. I'll just post the video over here. Actually, I can just post the video directly as well. So like he also explains it using um, assembly as well. So yeah, okay. Now that that's out of the way, so how would a stack frame look like? So now that we like have an idea, we have the stack frame, the stack pointer, which points to like a spot. We can manipulate the stack pointer. Well, how would it look like? So let's go to over here because I'm pretty sure I do have a copy. So again, if you want this slide, this paper, it's in the Discord. So you can Discord notes. It should be course 341, chapter 2. So you can go into that the notes section just to show you one last time. The notes section, it's right over here. Okay. So if you're using the color safe strategy, the activation record layout would look like this, where the top you'd have the remaining incoming parameters, and then here you'd have the first incoming parameters, the return value, and which is also the return value, and the return address, and the space for storing local variables. Oh yeah, I forgot to mention that activation records, it's like also stores the return values. So to explain this, um, when we're storing our parameters, let's say we're calling function, let's say we're calling function f p1, p2, p3, and p4. When it's stored in memory, I believe it would be stored p4, like in the thing p3, p2, and p1, and then followed by the rest of the memory like that. And then the first incoming parameter. So this would be like the first incoming parameter. We'll get to the return value. And then we have the return address. And the return address is usually just the label of the label of the color function label. Not the color function label, but the label because where we call the function in the call sequence, there's a label there. So it would like let's just say call sequence label. uh, And then of function of caller where we call the function. And then space for storing local variables. So if if we wanted to save, since if we're calling a function, we can like store all of our like variables over here. So if we had like we wanted to we had like let's let k be the number of registers. Here you'd have like k elements as here, so you'd have register one or register two and register three and register four. So this is how like the stack frame would look like. This is the information would have as well. And depending on like the memory address, we could be pointing like so when we're dealing the memory address could be pointing at this variable. So each one would be on its own block as well, similar to how like this one is. So the data here would take up however many it needs to take up over here, depending on how many variables. And k in this case represents the number of registers, I think. And so that's how the stack frame for the caller safe looks like as well. Do note that this screenshot was taken either for like the second edition of the textbook, so the third edition might look different or not. I don't see why you would change it, but that's it. So I'll just post this over here as well. So any question about this or like anything, assuming everybody's good. Oh, yeah. So that's how the information would be stored. And oh, awesome. Thank you. One detail I forgot to mention is that like another thing you can also to let's say this was like memory address like let's say this was like a memory address 15. uh, So to access this, you just say M15, and then M15 would just return K4, something like that. So if you wanted to store a variable in memory address 15, you just be like this equals to whatever is in variable. Let's say K4 is variable V. So whatever values in V would just be like stored as like let's say 12, the value 12 was in V. So, just like foo, and something like that. So it would be like that. So that's how it would look as well. So when I say K3, K2, you can just think of it as actual values, but you can just give it as like placeholders as well. So that's how you access memory and such. So when you see M something, it refers to that, and you can also store that something as well. So that's the data structure, at least the stack frame for this. And why is it important? Because when you're writing your call sequence and all of that, you'll be doing some mathematics. But when I say math, you're just counting or like usually there's a standard size for a stack frame, or it could be dynamic, depending on that. I think the textbook does like a standard size, and you have to do some. I'm not too sure actually. I cannot comment on that, but that's the main idea. And yeah, so now that we have the stack frame, this is the stack frame for the caller save. What would be next? Believe we would have the caller save call sequence. So you can do a direct translation. So um, if you are to convert the call sequence for the thing, so you just do a screenshot. There you go. Copy. Okay, Firefox is just be Firefox again. Okay, Firefox. Okay, done. So how would an example? So with this, so this is how the stack frame for the caller save. I'm just gonna copy this so that we have a section for caller save. Caller save. So translation. This. So this is how the stack frame would look like. And now let's have this. So we have the calls sequence. Well, so when you're like translating after chapter 6, you'll have this line of code. So how do you translate this line of code over here in the caller save? The first thing is that you'd have these variables, these parameters over here, and then you'd have the call sequence. What you would do, at least how it would turn out or how it would come out, like this over here. So remember, So let's remember like how the caller save works. That function A would read all the use variables and save them into main memory, right? And then it would set the return value and then jump to function B, and then function B will use the registers and restore that. So that means like in our call sequence, it would be response. So the call sequence replaces the function call. So before we jump to another function, here's what we're going to do. We're going to save all of the, so we're going to read all the registers that we're using and save them into main memory. And so we're going to use these over here. So this just saves all of the variables that we're using. So that means like before we would have been using like R5 or whatever, really like then we would store each one. So you're going to like iterate through, let's say K is 5, then you're gonna have RK equals to 1, 2, 3, and 4, 5. And you'll notice that you have 4 times K. This 4, it represents the size of the stack. So remember the stack pointer points to like the stack pointer is this, it points to like a value over here. For example, it's going to point to 9. So we want to manipulate. So if we're storing a variable, let's say we're storing it in, okay, it's sometimes it's not usually this simple. Sometimes it's just like memory address 24, memory address 20, memory address 16, and memory address 12, and memory address 9, I think. 9, that's no, it's 8. It's 8 and 4 and then 0. At this case, you're out of memory. So you would, and let's say each variable. So I think it's 4 because this it's a byte, I guess. So maybe that doesn't, it doesn't really, the textbook doesn't, at least the second edition doesn't explain. So you would store like the number 4 or whatever. So you would store like you would store R0 here, and then you would store R1 here, and then you would store R2 here. Then you would store R3. That's not how it does. You store R3 here. Well, so let me just click over here, do this. Okay, I have to, very hacky. So you notice that see MCP. Let's assume that MCP is currently pointing at 24. So it would say M24, this, and then that, and then this, and then that. What's the call you save? See, remaining incoming parameters. Okay, let's say like SP is currently pointing at space for storing local variables. All right, let's assume this first. So let's assume like there's more like because um assume that it's pointing here, right? So that means like before we store this, let's say we have what's for so we have 28, and then we have 36, so 32, yes, and then 36. There you go. And then here we stored the so space, and then here we have the return address. So let's say function A was called by a different function or something like that. Let's go as function X. So this would have the label to return to that. And then the label for function X, so we'll just call it label X or something like that. And then 32 would store the first incoming parameter. Let's assume that it only had one parameter, P1, and then the remaining incoming parameters. Uh, yeah, no, let's just say P2. Might as well. It doesn't really matter. Doesn't really matter. So here we're in the section. So this is the call stack. So each function call would have its own stack frame. But here, this is the stack frame from R. Let's assume there's more variables here, but we're only concerned about this bit. Now we've stored all of these variables over here, right? And what do we do next? So we're also storing the function parameters as well. So these are, so when we pass in like these variables, we're going to store the value. So if we store like value 2, comma 4, comma 6, we're going to store these into the next stack frame. So we're gonna, let's assume we only have just two, passing in only two values. So let's say we only have A1 and A2. So that means we're going to say what? What are we going to say? We're going to say yeah. Okay, wait. Give me a second, you guys. I'll be back. Sorry about that. My nephew was calling. I could not ignore him. Uh, okay, where was I? Here. So over here in this bit of code, but is everybody following so far? Did I miss anything? Like, is everybody understanding what's going on? Yes, Ethan said yes. You guys can do your reaction. Oh, no, it's barely here. So if you're not understanding, you'll get to me later. So I'll also upload the video as well. So you get this over here, and then you have this bit of code here, and this changes the stack pointer. And the way this works is that sp minus 4 times n plus 1. What is n in this case? N is the number of arguments in here. So this is 1 dot 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 n. So in our case, let's say n is 2. So it's going to be 2 plus 1, which gives us 3 times 4, which gives us 12, which gives us 12. 12. So, and then, so this bit equals to 12 minus SP. What is SP in our case? SP is pointing to 24. So we're going to say 12 minus 24. No, no, it's 24 minus 12, which gives us 12 again. So this takes us all the way down. So the stack pointer goes from pointing to here to uh, going pointing to here. And yeah. Okay, I feel like I'm doing something wrong. Okay, just move this so it's pointing here now. Hopefully I did that right. Okay, okay, see. And then MSP plus 4. So what? Plus 4. Let's see. I feel like I did something. MSP plus 4. Yeah, I do feel like I did something wrong here, like really wrong. Okay. Okay, K. No, K, we said our K is 0, 1, 2, 3. So we have 4 registers, so our K is 4. So I made a mistake. So we're looking at, so K is 4. Uh no, just see. What was I looking at? I feel like I lost myself somewhere. SP minus 4 times n plus 1. No, I did it right. Did it right. Oh, that's not supposed to happen. Let's see. In this case, uh yeah, okay. SP, yeah, yeah, I did my math wrong. I did something wrong. So I think I did it in reverse order. I was not looking because when you're adding your registers, you're adding. So I've here it's supposed to be, I think, like so. Yeah, it's supposed to be something like that because register one is stored at SP. Was it? Yeah, yeah, yeah. Okay, our stack pointer should have been pointing at the bottom, and then it would have been adding upwards and such. So I made a mistake there as well. I was not looking. I was not looking. But it's still the idea is still the same, where you have like some empty space and then you're just adding. And then from here, when we do the math, like once you've done this bit over here and you've added upwards, because again, when you add to your SP, it takes you up. So when we do our math and we say minus, so we do this, we get 12, it takes us all the way to 0. as well. And then from there, you'll start like populating the values like so. And then from there, I think you think that's what that's what this bit does. And then you have your return address, and you notice that your return address is the same as the label over here. All right. And so you set the label at let's see, SP plus 4 times N. Let's see, MSP plus 4. Oh, no, I did it again. I'm supposed to add. So this is supposed to come at the top over here. And then the return address is just supposed to be a return address. Supposed to be that. Because the reason I'm moving these up is because we said like SP got moved to SP is now 0. So when we say 0 plus 4, we get A1. And then A0 plus 8, we put them over here. And then this over there. Right? And then once that is done, we go to G. And G is the function that we're calling. So when you have your function definition, so when you define your prologue, that's where the label G is. And then, yeah, let's see. So where your label G is, and then you have label return address. And then, so this is just like, so this is just the instruction, and this is the label. So once we go here, in the epilogue where the label for like for this for function G is, we're gonna return to this one as well. And then x equals to msp plus 4 and sp plus 4. So sp, I'm pretty sure G is going to change sp somehow. Um, but once we return it, so but sp will be a value such that we'll be able to like x okay x equals to msp plus 4. I don't know what x is. Hmm, yeah, I don't know what X is. Well, I'll just put a question mark. It's that I forgot. I don't know what the compiler construction version of a magic number is, but whatever X is, it's that. Um, SP equals to as 4 times n plus 1. Doing this should take you back to like where where it was. I think it should be pointing to here as well. Like if you do the math again, it will just take you to over there. And then you have SP. So, and then you just restore. So you notice that it's going to be S0 equals to MSP. So over here, we're returning the value. So it's doing the very opposite of this over here. So that's how you convert this into this. Like, so a little bit of math, but the math is just it's simple enough if you understand the stack frame and enough so you can refer to this or you can watch the YouTube video here, how functions work in assembly. And hopefully it's the video I'm thinking about because let me just double check it to be on the safe side because I know it's still good. There was a video where he just explains like how much the at least how memory works if you want to see it in action yourself. But the idea is still there. You can still go through it and such. So that's how when you convert. So when we look at this example over here, this call sequence over here, when we translate it, it will translate into that. I'm looking for just a function call. So you have the call sequence and the caller save. Then you're gonna have your go to G. You're gonna have those, and then you're gonna have like the variables that you have. So you're gonna have MSP equals to all of this, all the variables that we're using. Then you're gonna have SP equals to this, and does this explain? I don't know. Retrieves the return address or the return value. Oh, yes, 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 yes. Okay, yeah. The X here is this value over here. All right. So another thing I forgot to mention is that, over here, remember that like when we're storing the values, we have all of this, and the first incoming parameter says all return value as well. So the return value is the same place. So the return value will is also where we store the first parameter. So when we're done executing, like the function is done executing, let's say we have a function that has a return value. That return value will be stored where the first parameter is. So we just overwrite what the first parameter is, and we just place the return like that. So like if it's like y. So this x over here comes from x equals to call g equals to 1. So yeah, that's where it comes from. So that's the return value. So this is the return value. We're getting the return value. We're setting it into x. Why x? Because that's like the original thing over here. So hopefully that makes sense to people. And yeah, so okay, I'm glad. So this website very useful. I love it. Right. And then yeah, so this stores also it sets up all the variables. It gets the return value. It goes to the function's code, and then it does the reverse. So it just goes back into reverse. So is everybody understanding how they would translate this? At least like the call sequence. Yes. Okay, good. So uh, you can also do reaction type matter. So if you still don't get it, I'll upload the video. You can watch it again. I did make a few mistakes, but the idea is still there, where you just have these. It's not too complicated. Like the chapter 9 is not. I think it suffered from like lack of examples or such. But yeah, that is that. There's the call sequence for the function call. And you can see how like the structure of this matters. So if you understand how this is structured, you know how this. But this structure is specific to caller save, and callee save has its own structure as well. And now we're going to look at chapter not chapter not introductory, the prologue. So the prologue is the header for the function using the frame layout. So we're just going to take this over here, paste it, paste it, frame size. I just make that variable. So why? So again, now go back to. Oh yeah, let's just to rehash, just to like let's refer back to this over here. So sets the label for the return function and a go to the call function. So see, it has all of these, right? And I should also say that it also saves the local variables, but it doesn't really matter for now. Uh, let's see. So now the call sequence you understand, you can see how it works. Now the epilogue. We're gonna do the epilogue second. Let's do the function header first. So I'll just do this so that you. So we're gonna do the function header. For now, okay, there you go. So the prologue is the header, the function header of the function. Okay, I'm starting again. So this is the where you just translate like I don't know like it's just like example. I'll just add an example here. So here you're doing like a function call. You're translating the function call, and here you can translate the function like the function, depending on which language you use. Like I think F is a bad name. Like fun is a bad name. Uh, foo. So we're just translating this bit over here. So depending on the language as well. And it assumes that it has A and B. And then this just returns, like it just translates to return. And yeah, you can just put in the call. Yeah, that's what we're translating. So now we're gonna look at this the function header, and this just A and B. We're just saving that. And we're gonna look at caller save first. So the caller save, jump to function B. Function B will use the registers and jump back into that. So function B will get the parameters and then it will save them up. So let's see how it does that. So the function header for caller save, fairly simple. Label F, will just be the label of the function, which is the function name. P1 to Pm. M is the number of parameters that function M has. Oh yeah, the function has. And then we're gonna start sp plus 4 and then sp times 3. And this, so over here, so assuming that this is for function M, it would store those variables like so it would basically be responsible for setting these values over here. Yeah, the top bit as well. So we're just setting the function parameters as well, and then the stack pointer frame size minus the frame size. The frame size, the frame size, the frame size is usually the size of the frame. I mean, that's in the name. It's usually the size of the frame, and you want to be so. Once you've set all of this, right, you're going to go all the way down. You want to go, at least it's better to like do your computations from here so that like okay, it's much better like to have the stack pointer always pointing at the bottom. So I'm guessing they might subtracting the frame size to do that because I'm guessing initially, okay, it's at a position where you're gonna be at the bottom and then you make your way up. At least when you're saving, you just save up, or at least when you do a function call as well. So the stack pointer sets it such that when you do your function call, you can just say sp equals to this. All right, so you can leave it like that or so, just but you'd have to be considerate, like where the stack pointer is. The frame size, let's say you're in an exam, can you just say frame size? Do you have to know the exact? You don't have to. It's different. You can just say frame size. So if Professor Green is mocking you, you can just say frame size, he'll know frame size for function f, or something like that. It doesn't really matter. You because even not even the textbook explains that like the actual frame size. It doesn't even explain where it gets the four. At least the second edition does not. So which the four is like the size of an integer, at least from like looking through. Um, but yeah, is that? So this is the frame. This is the prologue of a function. So yeah, when you have, let's say you have like you have an example like this. We'll go to the example. You have an example. This is the version that does not have the example. But luckily, I had it open over here. So if you have something like this, you would translate it into that. Like you would translate this part as well. And yeah. And so yeah, that's the prologue. I don't think there are any questions. Feel free to stop me if there is. But yeah, that's how you do the prologue. Uh, Relatively small. Then now we have the return statements. A function can have multiple epilogues as well, as opposed to the prologue. The prologue sets up the parameters and adjusts the frame size. The stack pointer. The epilogue like it does the opposite. At least it jumps back to the previous function and like unsets everything. But we'll see how that does. I'm just looking for the paper. A function can have multiple prologues as well. So we have return result. And pow. All right, there we go. So this translates into that. Bam. And yeah, not much to say really. S plus SP frame size. Again, addition takes it all the way up. It sets the return. So if it takes it all the way up, it takes it into like such a position such that like let's say in this case, let's say because I'm pretty sure when you're at your epilogue, your stack pointer is pointing to like at the bottom also. I'm not too sure. I don't remember to see. So let's say it was this situation over here. It would like you'd add the stack pointer, and if you do the math, like it would add you like it will have you maybe at this position like so. Yeah, it would have you at this position where it's pointing at the stack pointer because you can just say go to SP, just take me to SP, and then before since like is so this takes you to the label is the return address, and right above the return address is our sorry, I was like when right above the return address is our first as a parameter or our return value. So what we do there is that we say +4, which takes us above the label, and then we just go to MSP, and that takes us to that. And that's how you do your epilogue. So every epilogue for your function will have that, like will have that. So this I should just be showing you like the actual examples of it as well, like this one. So over here you have return one, return zero, and yeah. So when we look at this, we have return one, return zero. When you look at the actual translation, like label label L1, label L1 under label L1, you're gonna have this. Exact. So it's frame size even underscore even, as you can see. So, hey, I did a good job of highlighting here. But yeah, so that's how you do it for caller save. So does that make sense, everybody? Does that explanation like well, make you understand? Because that's like the caller save section, and the callee save is the exact same, just it does it differently with a different stack pointer. So, but does that make sense overall, or like, is there any question? So, uh, okay, where did I lose you? Okay, is that basically a general format of how everything is supposed to flow? Uh, okay, I'd say like my ex. Oh, are you referring to? Because there are two things here. Just waiting for Ethan to finish typing. Yeah, I'm just gonna wait a bit. Um, is everybody else all right? Like, and you just substitute the specific question parameters. I'm talking about the entire calling from start to finish. Okay, is that basically a general format of how everything is supposed to follow, and then you just substitute the specific question parameters? Okay, you might have to emphasize the question parameters. And I'm talking about the entire call and callee save from start to finish. Okay, is there a flow? Did you want to know, like, you want to know how you would go from like how would you apply the caller, at least caller or callee, onto an intermediate code to get a value? Okay, uh, so okay, uh, in case so for everybody, the method just like before I carry on is does the method itself like the way you translate this make sense? Like, does the strategy for everybody can like throw a thumbs up or like a zero before I explain the whole thing? Okay, he's good. It's good. Because yeah, I would go through for the sake of time. I don't think I'll go through call Lee save, but it's the same thing. The only difference is that like the stack frame is different, and because the stack frame is different, and also like the order in which things are done is also different as well. But it's still the exact same thing, the exact same process, but not the exact same process, but the logic. Like for example, the callee save, the function that's being called is saving as well. Because I want to also do a bit of chapter 8 and also call it a day as well. if you again again you'll post a question or like add me on Discord if you like don't like if not, but if you're good now with this, let me explain. So let me just let me just copy the question. Is that general flow? Uh, is that a general flow for how everything is supposed to work? So in this case, let's say to just make use of this example. Okay, all right. So you get a question like so. Copy it. Let me drink some water. Mm, mm. Okay. So step one, at least the first thing you do, the flow would go something like this. You get a question, and um, let's just say let's just say step one. One question gives you code, asks you to translate using chapter 6 and chapter 9. All right. So what you do, these are not that's not a step. That's okay, just put it. Uh, what to do when the question gives you this. Let me just put it in a different section over here. Okay. What to do when question. So hopefully that's like a good subtitle. It's like a wiki article. So step one. Okay, step one, right? So let's put this over here. Step one, translate the code using the method from chapter 6. So you're gonna take this whole code, right? And you're gonna go through the tables. So the tables I referred to from the textbook in chapter 6. Chapter 6, interesting. Let's see. I believe it should be one of these tables over here. Let me just find the right one. I think could be these ones. So you just follow these. Yeah, I think it could be these. So you just follow these tables over here. Copy it. Again, this example was done using something from the second edition of the textbook. I don't know how different other than like it has extra chapters. Uh, chapter is, and so I get more tables. So you get the table specific. But let me get all the tables in case somebody just wants to. Did I copy the right table? It doesn't look like it. Hopefully, I remember there being a lot more tables, but I'm not sure how different they are. They could be the same tables. I don't know. But the idea is that you go from chapter 6, you find the grammar, the you find the tables for this grammar, at least for the this language over here, and then you apply them. Let's assume these are the tables. The tables. You take this and you put it through the tables, and put some thickness onto there. And when you follow the tables, you get the following. Right? Get the following, the intermediate. So by just following this, so you get the intermediate code. And I think it'd be better if I just copy it all. Stop that. Let me just copy this and then include the correction of. So you just get all of this. So I don't think it needs to be this big. Yeah, with this. So you're gonna get T0 equals to call, and you just get T0 like that. That's the correct one. Uh, Hopefully everybody's with me. Feel free to stop me if like this doesn't make sense, but you just follow the method. Again, I do have a YouTube video showing you how to do this as well. Then now that's the first step, right? And then step two. Step two, use a strategy for converting the call because not you can not also just to highlight. So not even though we're done here, right? We still have this that's untranslated. Let me just highlight the whole thing. All right, we have this that is not translated. That's a very bad color. That's a decent color. And this as well. That's still a bad color. And then you have the returns, the yellow. Okay, that's very very purple. There you go. And you have this, and then you have and then you have a function call again. What color did we use? Red for this. Okay, so let's go through it one more time. Okay, so now that you've translated, you have to translate these bits: the function header, the call statements, and the return statements, right? Choose a strategy to convert the call, return, and function definition. And the strategy could either be caller save, uh, caller save, or call save, right? And if you and depending on which one you pick, right, you would end up with like you just translate the the call sequence. So you just translate the call sequence. So you from here, this call sequence over here, you would just translate it using what we learned here. So your call sequence, you just do this. The register table, this table, right? Because there's the code itself, and then there's like the register table. This register table is just a mental model. It won't like it's just for you to understand. Okay, why am I adding? Because when you're entering, you're not allowed to add the dot 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 dot. You have to actually put in a number of things, right? So in our case, like when we look at this, when we translate, let's see. So in our case, when we translate using this, so you're gonna have this part. You're gonna have it's gonna translate into how the hell did it work again? Since okay, since it's T0, call is that a call thing? You're gonna have since it's a call statement, you would normally save okay, where do we translate? So no, it's a call statement. So you have like call even this, and then the way it would look over here. So you first start off by like saving all of the previous like variables. In this case, aren't any previous variables, so you won't have like you have not used any registers at all. And let's see. Okay, I keep getting lost. So you would not have like a caller save. Okay, you would not. Okay, you would have this bit up here. Yeah, like that. Just okay. This part would translate into this part. Yes. Okay, yeah. There you go. So this would translate into this MSIPI. Okay, this may be like wrong, not entirely wrong. It might be missing the T0 as well. That we have to account for, but it's roughly that. So you would translate this into that, and then you would translate this. And once you've like translated that, right, you're gonna take this whole bit and then you're gonna put it into here as well, and then you're gonna translate this part, the even, into its respective over here. You're gonna translate it into this, which you will get. Let me just close this and that. You would translate that into this. So you can imagine that the flows like as you go, you just like uh, yeah, you translate it into that, and then you would do the same thing for these as well, right? You take like the return statement. So this one over here, you just slap it on to here and such. So yeah, you would put in for this as well. I think do we still have it? I don't think so. I don't think we have the return statement. So this must have been turn one. Um, turn one. Okay, but is this making sense so far? Like what the flow would look like, at least like um, what you would translate the rest of these, like each part, and then you'd have the following full example, and then that would be your final thing, and then so you translate each part, and then I guess step three, um, yeah, yeah, okay, um, clean up, I guess, just clean up or like submit. Really, it's just two steps. Really. I don't. I'm hesitant to call it a two-step program, but yeah, this is how it would look like. Um, the fastest way to do this is like, so you can see how like if you were to like go back to like chapter 6, how would you do this fast? Uh, you can sort of see it. It's the same idea where you notice that this, if there's a function with no parameters, it would always produce this. A function with main parameters will produce that. So that's how it would like work. And it's like you'd understand the structure because over here I'm pretty sure the structure would still be the same. So while you're doing chapter 6, you can do chapter 9 as you're doing it, and yeah, because you realize that that's how you do it. So it's the same thing. So is everybody understanding how this chapter works? Like, does it? Okay, it's good. Is everybody happy with the session? I think we can do chapter 8 tomorrow around the same time and along with the other chapters that like you guys want to do. Um, is that good with everybody? Is everybody good with that? So, okay. Uh, I think I'll finish recording this. I'll upload it to my channel. Is there any questions like regarding chapter 9 or like what to do, what's going on there, or like anything confusing? Because this is the uh hopefully this like gives you an idea of how like it is and structured. Hopefully it was helpful in some way. It's like it clears things up. Sorry about that. Yeah, just waiting for we're going to finish giving feedback, questions. Yeah, okay, the only thing that we didn't do is the Collie save, but it's the same idea. And hopefully rewatching the video would help with that. Uh, Must be a really long question. So, uh, see, question for the math. For the math, okay? I know we only covered caller saves in class, so you think we should go over it? I just had a question mark. I know we only covered in class, so you think we should go over it or not? Oh, all right, can you repeat? Hmm. Uh, in which class? Like this class or uh, yeah, you might have to rephrase it. Like I do not understand. Okay, during the semester, I meant. Okay, you guys only covered color. Huh, that's for I don't remember if you also covered both or not. That mean go through color and collie, going through both of them would help, and also having examples of them in your textbook. In the book that the notebook would also help because it's good to have it like this, like side by side, where you can even look at this the way I did this over here. Just very simple. Just have the example for color save and then collie save, so you could have like your book split into this is how the color save looks like. The most important thing to understand is how to use the stack frame, like how the stack pointer is, because the stack pointer is not like eh, I'm not sure if like hopefully my explanation was a bit dodgy. I'd say because I was not giving because in last year's video I made use of Excel of Google Sheets to explain it because I could like actually move it around. But the idea is that if you understand how the stack works, like where the variables stay and like adding each one, that's the most important thing to understand. And once you understand the stack pointer and the stack frame and the frame size and all that, you can basically understand what this is doing. And also another thing as well is just having this hierarchy over here and just understanding some of the notes. I would suggest going. I'm gonna try saving this board, but I'm not sure if I'll be able to like again because I've had trouble before trying to save the board. But yeah, having like this idea over here of like function A, like a high level example, and then looking at the stack pointer, and then looking at this does help. And then having these examples in your textbook, in your not textbook, in your notebook. Mhm. Oh, so yeah. Hopefully, is there anything else from anybody else, or anything really like this before we clock off? Or was it a good session? Did it help? Um, okay, that's a consensus is good. I'm glad. Thank you guys for coming along, and I'm glad this helped. Hopefully, in the exam, it's with compiler. I know it can be a bit intimidating, but it all boils down to simple examples. And usually, chapter 6, 9 questions are just like this is the basic flow. Just you're just translating certain bits, and why you're doing it is because it's not supported and such. And yeah, today we did, let's see, let's see, just okay, just looking at something. Yeah, this thing over here. So we covered this and this. Yeah, take your time to practice, like different examples as well. Then yeah, yeah. What else? So we'll cover the rest. I'm not sure if we'll be able to cover everything, but I do have a video on the other chapters except 4 and 5. I only have video for this. So tomorrow we can do anything else, like another session. It usually takes me, I can cover 3 chapters, at least like explain, run through as well, depending on what they are. Chapter 6 and 9 are just the longest. So tomorrow we can carry on with that. If you want, if you want to know how to do things fast or such, you can again go through here, ask a question. I do try to answer it, and then what I like about this is that everybody can see and like comment, and like if something is wrong, they can just say something's wrong, and the notes section as well. If you feel like sharing something or like you understand something as well. And yeah, thank you again. I appreciate you taking the time to join and see you tomorrow. There'll probably be, it's the last session, of course. And good luck in studying.